When you have to deal with angular momentum for particle, use this. Angular momentum for a system of particles or body, use this. We were talking about the conservation of angular momentum. If you have a system and if there is no external torque acting on it, then L will be constant. That is the meaning of principle of conservation of angular momentum. Say for example, some disk is rotating about this axis. Its angular velocity is omega, its moment of inertia is I. Now suppose you press the remote control and two particles which were originally inside it, or let me say something which was inside it, that thing comes out. And now it starts looking like this. These things were earlier inside and now they have come out because you triggered that motion. You did not apply any torque. You just pressed remote control, and due to the internal design of it, these fellows came out. So it could be internal stresses in the system giving rise to this type of thing. Just like you make your hand straight due to the internal stresses in your body, you are able to make your hand straight, just like that. And when you do that, this thing was earlier inside, so all those particles were closer to this axis. Likewise here also. These particles were closer to this axis. Now these particles are further from the axis. So this I on the right side will be more than this I on the left side. But then there is no external torque. We are ignoring the friction. Ignore the friction present in the axle. No friction in the axle. So no torque external. And that means I omega will be constant. Now if I is more, then omega has to be less, and only then can I omega be constant. So its omega automatically decreases. So that's an example of conservation of angular momentum. We have a rod rotating about an end, about an axis perpendicular to its length. Mass of the rod is given, its length is given, its angular velocity is given. First question, what is the angular momentum of the rod about this axis of rotation? You are dealing with body here, so you must use L equal to I omega. What is I for the rod about this axis? You know that. You can use parallel axis theorem. What about the unit? Unit can be found from the definition or from simple MVR. And the answer I have is 0.05 kg meter square per second. L equal to 0.2 does not make sense unless you specify the unit. Now, if you would like this to be discussed on the board, then raise your hand. Okay. I equal to ICM plus M distance square. So we have ml square by 12 plus m L by 2 square. So ml square by 3. So ml square by 3 multiplied by omega. Now you just need to put the values. Let me know if you still have any questions. Alright, now the part B is that what is the speed of the center of mass of the rod? It's a uniform rod. It's a uniform rod. So what's the speed of the center of mass of the rod?